C is a general-purpose, imperative computer programming language, supporting structured programming, lexical variable scope and recursion, while a static type system prevents many unintended operations. By design, C provides constructs that map efficiently to typical machine instructions, and therefore it has found lasting use in applications that had formerly been coded in assembly language, including operating systems, as well as various application software for computers ranging from supercomputers to embedded systems. C was originally developed by Dennis Ritchie between 1969 and 1973 at AT&T Bell Labs, and used to re-implement the Unix operating system. It has since become one of the most widely used programming languages of all time, with C compilers from various vendors available for the majority of existing computer architectures and operating systems. C has been standardized by the American National Standards Institute since 1989 and subsequently by the International Organization for Standardization. Design. C is an imperative language. It was designed to be compiled using a relatively straightforward compiler, to provide low-level access to memory, to provide language constructs that map efficiently to machine instructions, and to require minimal runtime support. C was therefore useful for many applications that had formerly been coded in assembly language, such as in system programming. Despite its low-level capabilities, the language was designed to encourage cross-platform programming. A standards-compliant and portably written C program can be compiled for a very wide variety of computer platforms and operating systems with few changes to its source code. The language has become available on a very wide range of platforms, from embedded microcontrollers to supercomputers. Overview. Like most imperative languages in the ALGOL tradition, C has facilities for structured programming and allows lexical variable scope and recursion, while a static type system prevents many unintended operations. In C, all executable code is contained within subroutines, which are called functions. Function parameters are always passed by value. Pass-by reference is simulated in C by explicitly passing pointer values. C program source text is free format, using the semicolon as a statement terminator and curly braces for grouping blocks of statements. The C language also exhibits the following characteristics. There is a small, fixed number of keywords, including a full set of flow of control primitives. For if, else, while, switch, and do, while. There is one namespace, and user-defined names are not distinguished from keywords by any kind of sigil. There are a large number of arithmetical and logical operators, such as plus, plus equals, plus, and tilde, etc. More than one assignment may be performed in a single statement. Function return values can be ignored when not needed. Typing is static, but weakly enforced. All data has a type, but implicit conversions can be performed. For instance, characters can be used as integers. Declaration syntax mimics usage context. C has no define keyword. Instead, a statement beginning with the name of a type is taken as a declaration. There is no function keyword. Instead, a function is indicated by the parentheses of an argument list. User-defined and compound types are possible. Heterogeneous aggregate data types allow related data elements to be accessed and assigned as a unit. Array indexing is a secondary notation, defined in terms of pointer arithmetic. Unlike structs, arrays are not first-class objects. They cannot be assigned or compared using single built-in operators. There is no array keyword in use or definition. Instead, square brackets indicate arrays syntactically, for example month, 11. Enumerated types are possible with the enum keyword. They are not tagged, and are freely interconvertible with integers. Strings are not a separate data type, but are conventionally implemented as null-terminated arrays of characters. Low-level access to computer memory is possible by converting machine addresses to typed pointers. Procedures are a special case of function, with an untyped return type void. Functions may not be defined within the lexical scope of other functions. Function and data pointers permit ad hoc runtime polymorphism. A preprocessor performs macro definition, source code file inclusion, and conditional compilation. There is a basic form of modularity. Files can be compiled separately and linked together, with control over which functions and data objects are visible to other files via static and external attributes. Complex functionality such as I/O, string manipulation, and mathematical functions are consistently delegated to library routines. C does not include some features found in newer, more modern high-level languages, including object orientation and garbage collection. Relations to other languages. Many later languages have borrowed directly or indirectly from C, including C++, D, Go, Rust, Java, JavaScript, Limbo, LPC, C#, Objective-C, Perl, PHP, Python, Verilog, and Unix's C shell. These languages have drawn many of their control structures and other basic features from C. Most of them are also very syntactically similar to C in general, and they tend to combine the recognizable expression and statement syntax of C with underlying type systems, data models, and semantics that can be radically different. History. Early developments. The origin of C is closely tied to the development of the Unix operating system. Originally implemented in assembly language on a PDP-7 by Ritchie and Thompson, incorporating several ideas from colleagues. Eventually they decided to port the operating system to a PDP-11. The original PDP-11 version of Unix was developed in assembly language. The developers were considering rewriting the system using the B language, Thompson's simplified version of BCPL. However, B's inability to take advantage of some of the PDP-11's features, notably byte addressability, led to C. The development of C started in 1972 on the PDP-11 Unix system, and first appeared in version 2 Unix. The language was not initially designed with portability in mind, but soon ran on different platforms as well. A compiler for the Honeywell 6000 was written within the first year of C's history, while an IBM System 370 port followed soon. The name of C simply continued the alphabetic order started by B. Also in 1972, a large part of Unix was rewritten in C. By 1973, with the addition of struct types, the C language had become powerful enough that most of the Unix's kernel was now in C. Unix was one of the first operating system kernels implemented in a language other than assembly, and MCP for the Burroughs B5000 written in Algol in 1961. Circa 1977, further changes to the language were made by Ritchie and Stephen C. Johnson to facilitate portability of the Unix operating system. Johnson's portable C compiler served as the basis for several implementations of C on new platforms. K&RC in 1978, Brian Kernighan and Dennis Ritchie published the first edition of the C programming language. This book, known to C programmers as K&R, served for many years as an informal specification of the language. The version of C that it describes is commonly referred to as K&RC. The second edition of the book covers the later ANSI C standard, described below. K&R introduced several language features: standard I/O library, long int data type, unsigned int data type, compound assignment operators of the form equals op were changed to the form op equals to remove the semantic ambiguity created by such constructs as I equals -10, which had been interpreted as I equals 10 instead of the possibly intended I equals -10. Even after the publication of the 1989 ANSI standard, for many years K&RC was still considered the lowest common denominator to which C programmers restricted themselves when maximum portability was desired. Since many older compilers were still in use, and because carefully written K and RC code can be legal standard C as well, in early versions of C, only functions that returned a non-int value needed to be declared if used before the function definition. A function used without any previous declaration was assumed to return type int if its value was used. For example, long sum underscore function, asterisk int asterisk, calling underscore function, if test2 equals 0, else test2 equals other underscore function could check for consistency of function use across multiple source files. In the years following the publication of K and RC, several features were added to the language, supported by compilers from AT&T and some other vendors. These included void functions, functions returning struct or union types, assignment for struct data types, enumerated types, the large number of extensions and lack of agreement on a standard library, together with the language popularity and the fact that not even the Unix compilers precisely implemented the K&R specification, led to the necessity of standardization. ANSI C and ISO C. During the late 1970s and 1980s, versions of C were implemented for a wide variety of mainframe computers, mini-computers, and microcomputers, including the IBM PC, as its popularity began to increase significantly. In 1983, the American National Standards Institute formed a committee, X3J11, to establish a standard specification of C. X3J11 based the C standard on the Unix implementation. However, the non-portable portion of the Unix C library was handed off to the IEEE Working Group 1003 to become the basis for the 1988 POSIX standard. In 1989, the C standard was ratified as ANSI by 3.159-1989 Programming Language C. This version of the language is often referred to as ANSI C, Standard C, or sometimes C89. Therefore, the terms C89 and C90 refer to the same programming language. ANSI, like other national standards bodies, no longer develops the C standard independently, but defers to the International C standard, maintained by the working group ISO, i.e. CJTC1, SC22, WG14. National adoption of and update to the international standard typically occurs within a year of ISO publication. One of the aims of the C standardization process was to produce a superset of K and RC, incorporating many of the subsequently introduced unofficial features. The Standards Committee also included several additional features such as function prototypes, void pointers, support for international character sets and locales, and preprocessor enhancements. Although the syntax for parameter declarations was augmented to include the style used in C++, the K&R interface continued to be permitted, for compatibility with existing source code. C89 is supported by current C compilers, and most C code being written today is based on it. Any program written only in standard C and without any hardware-dependent assumptions will run correctly on any platform with a conforming C implementation within its resource limits. Without such precautions, programs may compile only on a certain platform or with a particular compiler, due, for example, to the use of non-standard libraries, such as GUI libraries, or to a reliance on compiler or platform-specific attributes such as the exact size of data types and byte endianness. In cases where code must be compilable by either standard conforming or K and RC-based compilers, the __stdc_ macro can be used to split the code into standard and K and R sections to prevent the use on a K and RC-based compiler of features available only in standard C. After the ANSI ISO standardization process, the C language specification remained relatively static for several years. In 1995, Normative Amendment 1 to the 1990 C standard was published to correct some details and to add more extensive support for international character sets. C99. The C standard was further revised in the late 1990s, leading to the publication of ISO, IEC 9899 to 1999 in 1999, which is commonly referred to as C99. It has since been amended 3 times by technical corrigenda. C99 introduced several new features, including inline functions, several new data types, variable length arrays and flexible array members, improved support for IEEE 754 floating point, support for variadic macros, and support for one-line comments beginning with as in BCPL or C++. Many of these had already been implemented as extensions in several C compilers. C99 is for the most part backward compatible with C90, but is stricter in some ways, in particular, a declaration that lacks a type specifier no longer has int implicitly assumed. A standard macro __stdc _version _ is defined with value 1999901L to indicate that C99 support is available. GCC, Solaris Studio, and other C compilers now support many or all of the new features of C99. The C compiler in Microsoft Visual C++, however, implements the C89 standard and those parts of C99 that are required for compatibility with C++11. C11. In 2007, work began on another revision of the C standard, informally called C1X, until its official publication on 8 December 2011. The C Standards Committee adopted guidelines to limit the adoption of new features that had not been tested by existing implementations. The C11 standard adds numerous new features to C in the library, including type generic macros, anonymous structures, improved Unicode support, atomic operations, multi-threading, and bounds-checked functions. It also makes some portions of the existing C99 library optional, and improves compatibility with C++. Embedded C. Historically, embedded C programming requires non-standard extensions to the C language in order to support exotic features such as fixed-point arithmetic, multiple distinct memory banks, and basic AO operations. In 2008, the C Standards Committee published a technical report extending the C language to address these issues by providing a common standard for all implementations to adhere to. It includes a number of features not available in normal C, such as fixed-point arithmetic, named address spaces, and basic AO hardware addressing.